Hello, class. My name is Peter Marzo, and today we'll be talking about the proton NMR spectra for both ethanol and ibuprofen. When talking about the proton NMR, it is important to take in a few things into account. The number of signals, the position of the signals, the integration of the signals, and the spin-spin coupling between these signals is all important. So first, let's get into a bit of information about NMR specifically. NMR stands for nuclear magnetic resonance, and there are two types of NMR that can be used to help determine the structure of a compound when it is not already known. Proton NMR, or 1H NMR, is used to determine the type and number of hydrogen atoms within a molecule, whereas proton NMR, or 13C NMR, is used to determine the number of carbons in, or the type of carbons within a molecule. However, we will not be using carbon NMR in this video. When examining proton NMR, I like to start with the number of signals first. So there are three different signals for ethanol. There's one right here, which is labeled 1, second one, which is labeled 2, and third one, which is labeled 3. They're all at different locations on the spectrum, and they all have different shapes. So let's get into the shapes first. Each of these locations, or each of these things, is called a signal, and they all can have different shapes. The shape of the signal is determined by the number of hydrogen atoms on the neighbor of the certain signal you're talking about. So if there is a signal with 3 peaks, it means that the neighbor has 2 hydrogens. And if there is a signal with 4 peaks, it means that the neighbor has 3 hydrogens. The number of peaks is equivalent to the number of neighbor hydrogens plus 1. So when there is a singlet, as we see here for signal 3, it means that the neighbor has 0 hydrogens. And as we see here for signal 2, there are 4 peaks, which means that the neighbor has 3 hydrogens. As for signal 1, there are 3 peaks, and which means that the neighbor has 2 hydrogens. The names for the signals are pretty easy to understand. Signals with 1 peak are called a singlet. Signals with 2 peaks are called a doublet. Signals with 3 peaks are called a triplet. Signals with 4 peaks are called a quartet. Signals with 5 peaks are called a quintet. Signals with 6 peaks are called a sextet. Signals with 7 peaks are called a heptet. And signals with any more peaks beyond that are called multiplets. Next, when getting into the different locations on the NMR spectrum, these locations can signify different functional groups due to the presence or lack thereof of an electronegative element. So protons that are closer to electronegative elements will be further downstream and will have a higher ppm value, whereas those that are upstream will have a lower ppm value because they are further away from the electronegative elements. In ethanol, we can see that there is a singlet at around 3.75 ppm, and the integration shows that there's 1 hydrogen. Also, it is important to note that the integration for each of these signals shows the number of hydrogens on the specific signal, not the neighbor. So the shape of the signal will show the number of hydrogens on the neighbor, where the integration will show the number of hydrogens on the specific signal. So we can see here that signal 1 has 3 equivalent hydrogens, signal 2 has 2 equivalent hydrogens, and signal 3 has 1 equivalent hydrogen. Signal 1 is at 3.75 ppm, and it is a singlet, and the integration is 1 hydrogen. This would mean that the neighbor has 0 hydrogens, and it is downfield, which means that it is most likely directly connected to an electronegative element. It is also important to note that when given these spectra, sometimes the molecular formula will be included, which can show you if there is an electronegative element or not. However, when the formula is not included, it is important to pay attention to the position of these signals to show the presence of an electronegative element or not. So, since signal 3 is further downfield and it only has, and the neighbor has no hydrogens connected to it, I would believe that this is an alcohol. In addition to considering our spectra data sheet, which shows that anything within this region of 1 to 4 ppm could be a hydrogen attached to an oxygen or an alcohol. Next, moving on to signal number 2, this is around 3.6 ppm, and it is a quartet, and it also has an integration of 2H. In a quartet, there are 4 peaks, which means that the neighbor has 3 hydrogens. However, this is further downfield. However, this signal is further downfield, which makes me believe that this signal, that which is being specifically talked about with two hydrogens, is closer to the electronegative element or the oxygen as we determined from the last signal than any other or than anything else in the compound. So from these two signals alone, we've already determined that we have an alcohol functional group as well as a CH2 group right next to this alcohol. Next, the signal at 1 ppm shows a triplet, which means that the neighbor has two hydrogens, and the integration shows that itself has three hydrogens. As we just discussed with signal number 2, there were two hydrogens that have a signal of a quartet, which means that its neighbor has three hydrogens. And when combined with signal number 1, it shows that these two are neighbors. So we know that there's a CH3 connected to a CH2, which is then connected to an alcohol. This is the structure, or the structure that I just described is ethanol, and that is why these certain properties of this proton NMR spectrum are present. If any of these signals had been moved or the integration had been different, we would have been able to determine the structure for that compound as well. However, we're looking at ethanol and we can see clearly that there's a CH3 group, a CH2 group, and an oxygen and an OH group or an alcohol within this proton NMR spectra. Ethanol is a pretty simple molecule, and the proton NMR only contains 3 signals. However, much larger compounds like ibuprofen contain much more signals because there are much more different equivalent hydrogens. As we see here in this first signal, which I am circling with my mouse, we see that it is a singlet at around 11 ppm, and there's an integration of 1 hydrogen. This would mean that the position is this position, when looking at our spectra data, shows that there is a carboxylic acid functional group present, which means that this is a very electronegative functional group, which means that there will be much more shifting downfield in this molecule than before in ethanol. When looking at the next signal right here, we see that it is around 7.3 ppm, and it is a doublet, and it has an integration of 2 hydrogens. The neighbor would then have 1 hydrogen because it is a doublet, and itself has 2 equivalent hydrogens. In the location of the spectrum and the addition of there being an almost identical signal right next to it tells me that this could be a hydrogen that is on an aromatic group. As we see here in the spectra data, aromatic hydrogens are between 8 and 7 ppm, and this would fit perfectly with the position of these 2 signals on our proton NMR spectra for ibuprofen. Moving on to the 4th signal, we see a quartet around 3.65 ppm with an integration of 1 hydrogen. This would mean that the neighbor has 3 hydrogens, or a CH3 group, which I believe, and it is not necessarily directly downfield, and it could just be close to the carboxylic acid, which is very electronegative. So with a CH3 group and an integration of 1, I believe that the neighbor of this, or I believe that this signal is referring to a CH group connected to a methyl. Moving on to this signal here, we see another doublet with an integration of 2H at around 2.45 ppm. This shows us that the neighbor again has 1 hydrogen, but it is not the same 1 hydrogen from the carboxylic acid because it is too far upfield. Itself has 2 hydrogens, and I believe this is a CH2 group because it is not too far downfield, and it is most likely attached to a CH again, but this is different from the one that is attached to the methyl, as that one is also close to the carboxylic acid group. So this signal, just describing the doublet with an integration of 2H at around 2.45 ppm, shows that there is again a CH2 group within this molecule that is connected to a CH. However, it is not the same CH that is either, or it is not the same 1 hydrogen that is either in the carboxylic acid or the CH that is attached to the methyl group, as previously mentioned. Moving on to this smaller signal, we see here that it is labeled M, which stands for multiplet, meaning that there is abnormal coupling with this molecule. This is common in many big molecules, and it is important to notice that this is a larger molecule due to the number of signals that we see on the proton NMR, as well as the integration, showing us that there's 18 hydrogens, which is much higher than ethanol, which shows us only 6. So this multiplet shows us that there's a lot of hydrogens in this molecule, and this is a much bigger molecule than we've dealt with before. Moving on to the second to last signal, we see a doublet with an integration of three hydrogens at around 1.5 ppm. This shows us that the neighbor again has one hydrogen and itself has three. And this, I believe, is the opposite of what we talked about earlier with the CH group attached to the methyl, as we see here with this quartet with the one H integration. So a doublet with a 3H integration means that there are three hydrogens neighbored to one hydrogen, whereas a quartet with a 1H integration means that there's one hydrogen neighbored to three hydrogens. So these two are equivalent, meaning that it is confirmed that there is a CH connected to a methyl within this molecule. Lastly, moving to this larger signal, meaning it shows that there's an integration of 6 hydrogens in a doublet shape at around 0.9 ppm. This is the furthest upstream, meaning that it is the furthest away from any electronegative groups within the molecule, and it shows that there are 6 equivalent hydrogens, meaning that there are probably most likely 2 equivalent CH3 groups attached to a CH or attached to a CH group, because there is a doublet in the shape, meaning that this neighbor only has one hydrogen. So if there were two equivalent CH3 groups attached to a CH, that is called an isopropyl structure. And that is most definitely present in this molecule as shown by this NMR. After noticing the different partial structures that are present in this proton NMR, most importantly, the aromatic group shown by the 2 equivalent signals at around 7 ppm, the carboxylic acid, which is represented by the singlet at 11 ppm, and the isopropyl group shown by the doublet at around 0.9 ppm with a 6H integration, as well as the methyl group connected to the CH molecule, are all important for determining the larger structure of this. However, it is also important to note that there can only be 2 groups of equivalent hydrogens on an aromatic when there is para substitution, which means that the different groups attached to the aromatic compound or attached to the aromatic group must be at opposite ends of the ring. In addition to these partial structures, we also know that there's a CH2 group in this molecule, and this is attached to the CH group that is involved in the isopropyl group due to their corresponding signal information matching up with each other, and there being similar locations on the ppm, or them having similar ppms or locations on the spectrum. After looking at all these partial structures, in addition to the para addition on the aromatic group, you can include all of these structures and begin looking backwards at the proton NMR to see if these signals match up and to see if your structure you drew is correctly. When looking at ibuprofen, we can recognize all of these structures present in the proton NMR. First, the 1H, which is a part of the carboxylic acid, is present right here connected to this OH, or right here in this OH. Next, the 2 equivalent hydrogens, the 2 groups of 2 equivalent hydrogens are present on the aromatic group here and here and here and here. We can see this because the hydrogens attached to these 2 carbons experience the same properties as each other, and these 2 do as well. So there are 2 groups of 2 equivalent hydrogens on the aromatic. Next, we can see that there is a CH group attached to the methyl, which is shown by both this structure here at 1.5 ppm, and the structure shown at 3.6 ppm, or in the signal shown at 3.6 ppm. And this is shown right here in the molecule. Lastly, we have the CH2 group connected to the isopropyl right here in the molecule. And this is shown by the signals at 2.4 ppm, showing an integration of 2H, as well as the last signal at 0.9 ppm, showing its integration of 6H. So with all these partial structures, it can be determined that ibuprofen is a structure analyzed in the proton NMR above. Thank you guys for watching my video, and have a nice day.